Okay, so today we're going to talk about a quick video on how I implemented deferred rendering slash lighting into the AftrBurner engine. We're going to assume you already know a good bit of OpenGL, GLSL, how to render to frame buffer objects. We'll start by showing. So here is my normal forward rendering. You can tell because I've still got the axes on. I don't do that in the deferred lighting. There's deferred lighting, and it looks exactly the same. So how do you do defer? So what's the purpose of deferred lighting? For those that haven't heard of that. So deferred lighting, as I said, it looks exactly the same, is not like a lighting technique that inherently is supposed to make things look better. It is supposed to improve performance in certain situations, and therefore you can do more complicated effects, if you want to. So what situations does it improve performance? Not this one, because this one I've got like one cube and like one plane, and that's it. So the point of deferred lighting is for it to be an image order effect as opposed to an object order effect. So I've got two objects, not that big a deal. But let's say I've got 10,000 objects. They all have expensive lighting fragment operations going on, but not all of them end up on the screen at the same time in the end. You can do a constant time image order render, and maybe that improves your speed. And so how do we do that? Well, we know at the end, all we need to figure out the final fragment color at a pixel is the inputs to our lighting equation for that pixel once each. Assuming you don't have any sort of transparency and blending, in which case this isn't a good solution for that. How do we make sure we have, in this case, this is an 800 by 600 window. How do we have like exactly 800 by 600 samples for our vertex, eye space vertex, position, our eye space normal position, our depth information, our diffuse, ambient, and specular material properties. One sample per 800 by 600, as opposed to one material setting per object. It's like, well, if we render to multiple render targets, as we're doing a forward render pass, then we can get each of those samples that'll get depth tested and be unique, and then we can combine them in an image order step at the end. So let's see, I mentioned our eye space vertex position. So here you've got the objects that are larger in an x coordinate. That's why the red channel is higher. Here you have the positions that are larger in a y space coordinate. So their green channels populated. Here is negative in both, so it saturates to black. So then we do, let's say, our texel information. So here is, the raw texels we'd have in each spot. Here is the diffuse color we have in each spot. So we've got a diffuse color of, say, 0.1 for the cube here, and a 0.4 for the grass plane. But then if we go to like the ambient material, maybe we've got 0.1 for both objects, and so that's why they sort of blend together. And you've got, your specular channel. Here's depth information. So as I, get closer or further, you can see it changes. And then it's sort of one of the more interesting ones. You've got your eye space normal, which obviously the grass plane and the cube are both pointing up, so those are the same color, but the other ones, change as the eye position moves. So, each of these textures put together are what they refer to as the G buffer. Some people who may have tried to watch presentations on deferred shading before might have, based on some drawings, might have thought that like the G buffer was like some complicated render target that had a linked list of values in each texel. but it's actually a collection of textures, which you can see if I'm running NVIDIA Insight. So if I capture a frame and we come here, then you can see I've got this 7 different textures as input. And so next we should talk about, how do you generate those textures and how do you use them? Because like I said, I assume you all know how to use render targets, but you might not know how to use multiple render targets from the same shader. So we're rendering this object right now. So let's come here, look at the fragment shader, look at the shader code. You'll see our outputs. We actually have 6 different outputs from our fragment shader. This is not the vertex shader, this is the fragment shader. Often you'll have many outputs from a vertex shader for your fragment shader. In this case, we're actually having multiple outputs from a single fragment shader. And so our eye space position, eye space normal, the texel color, diffuse, ambient, and specular properties, and I'm shoving the specular coefficient in the 4th channel of the specular fragment there. And so once you run to actually draw your full screen quad, that will combine these. If we pop back over, you can see this fragment shader will have access to these 6 textures because depth is implicit. And so if we look here for our we've got these 6 samplers to our text unit, vertex eye space, normal eye space, color, diffuse, ambient. And then in our lighting equations, where we'd normally use our eye space normal, we just get the eye space normal from the texture. Where we'd normally use the eye space vertex, we get the vertex from a texture. Where we'd normally use our diffuse material, we get the diffuse material from the texture. So that is a straightforward example of how you generate multiple textures from a fragment shader to be consumed by another fragment shader on a full screen quad pass in order to do deferred lighting.